Hey everybody, here is FRQ number 3 from 2009. So in this situation, we've got two blocks attached by a string over a pulley. That pulley is massless, and both of these blocks have a mass of m over 2. Um, and they start from rest and then they're released. So part A just wants us to derive an expression for the velocity of the hanging block as a function of the distance that it descends. Okay, so a few different approaches here. Both are totally valid, and I'm going to do my work up here. Approach number one could be energy, all right, and approach number two could be forces. Okay, I'm going to go with the energy approach here because to me, energy makes things easier. So let's dive in with that. Now, looking at energy, the energy that block number 2 has right here is potential energy due to gravity, and the energy that it's going to have down here is kinetic energy. So let's just go ahead and dive in on that. All right, the potential energy that it has at the beginning is going to be equal to the kinetic energy that it has right there. So what we can say is that mgh is equal to 1/2 mv squared. All right. Now, looking at this, I know that the distance that it descends is d. So this is going to be mgd is equal to 1/2 mv squared. Now, here's kind of what's tough here. What is m here? All right. Now, m in this situation is referring only to that block because that's the only block that has a change in potential energy. This m is referring to this block and this block because both of them are moving. All right. So when we replace these and when we substitute these in, what we're going to get is, need that eraser, is m over 2 gd is equal to 1/2 times m over 2 plus m over 2 times v squared. All right. Now we can simplify this. So we get m over 2 gd is equal to, this is going to be 1/2. Yep, that's still going to be 1/2 m times v squared. And now look at this. Boom. These are going to go away. The 1/2s are going to go away. And what we end up getting is that v is equal to the square root of gd. All right, so energy makes our life easier there. Now, you could also do this the forces way. So I'm going to go ahead and talk through that with you guys because I think that's worthwhile for sure. And I'm just going to move this actually over there. All right, now I'm just going to erase some things. Okay, so let's talk through the forces method, okay? We know that Newton's second law is F net equals mass times acceleration. Now, in this situation, the net force is being caused by this mass right here, okay? Now, we've talked about this a little bit, but I can treat these as kind of one object here, where M2 has mg down, normal force up, and tension pointed this way. And if I stretched M2 out and I brought it up here, it would have mg this way and tension this way. These tensions are going to cancel, which is going to leave me with the net force of this system being caused by that mass. So what we're going to get here is that m over 2 times g is equal to the mass of the system, which is going to be m over 2 plus m over 2, times the acceleration of the system. All right. From this, we can solve for acceleration. And what we're going to get when we solve for acceleration is that acceleration is equal to g over 2. Okay. Now I have my acceleration. Let's think about what else I know in terms of kinematics. I know v initial is 0. I know that my change in position is d. And I also know, I don't know t and I don't know vf. All right. So I just need to pick a route, all right? I'm going to go with v final squared equals v initial squared plus 2a delta x because it doesn't have t in it, which is going to give me that v final is equal to v initial squared plus 2a delta x square root. And now we can start to make some substitutions into this thing. So vf is going to be equal to 0 squared plus 2 times g over 2 times d, which tells me that v final is going to be equal to the square root of gd. And I get to the same result as I did with energy. Either way works there, guys. All right, so there's A. Points on A. If you went with this method right here, this would have given you 1 point for that setup, 1 point for this substitution, 1 point for this substitution, and let's see, 1 point for this substitution. Notice no points came from the answer. In this method, you got 1 point for indicating Newton's second law. You got 1 point for solving for the acceleration. You got 1 point for selecting the correct kinematic equation, and 1 point for substituting d in for the distance. So notice all those points are just coming from the setup there. All right. Moving on to B. Determine an expression for the force of gravity of the hanging part of the rope as a function of y. So in this situation, we've changed the scenario. The block and pulley system has been replaced by a uniform rope of length L and mass m, and one end of that rope is hanging slightly over the edge. That rope is released from rest, and at some time later, there is a length y of rope hanging over the edge, as shown below. Express your answers in algebraic terms. So we need to figure out an expression for the force of gravity of the hanging part of the rope as a function of y. Okay, so force of gravity. I'm just going to do this down here. Let's start off with the basics. This is part B. I know that the force of gravity is equal to m times g. G is not going to be the issue here. The issue here is going to be what to do with m. All right, how do we account for that? So we have some portion of this rope hanging off the table. This portion right here, okay? So we need to figure out the relationship of this portion's mass to the overall mass, okay? So here's how we can think about this. Just think about it as a ratio. Total mass of the system divided by L is going to be equal to this portion of the mass divided by y. All right? I can rearrange this and solve for this m, which represents this mass. So that mass is going to be equal to m times y divided by L. We make that substitution down here, and that's going to be m times y divided by L times g is going to be equal to my force of gravity. All right? The key there was just a ratio between the portion of the rope that's hanging off to the portion of the rope that's the total. 2 points here for a correct expression. Okay? All of it rides on getting that correct answer. Part C, derive an expression for the work done by gravity on the rope as a function of y, assuming that y is initially 0. All right, so expression for the work done by gravity. So let's go ahead and approach C. We'll do this right here. I'm running out of space. Part C. So how do we relate work and force? Well, this is the work energy, or this is just the definition of work, which is that work is equal to the integral of f dx, and we'll call that f dy here. Okay. We know what f is. We just found it. So work is going to be equal to mgy over L dy, and that's an integral. And now we just need to solve this integral out. All right, so mg and L, those are all constants. Makes our life easy, right? So work is going to be equal to mg over L times the integral of y dy. That's a really easy integral. So that's going to be mg over L times 1/2 y squared. And boom, there's your answer. All right? Key there. Need to remember that work is the integral of force with respect to position. Points on this one. You get a point for recognizing that. You get a point for substituting your force from the previous problem. And you get a point for the correct integration. There's part C. Part D, derive an expression for the speed of the rope as a function of time. All right, derive an expression for the speed as a function of time. Okay, so let's again look at work and energy here. We're going to go down here, part D, because we just got an expression for work up here. All right, and work includes that. And I need to get to velocity. So I need to think about how I can utilize what I've got to get to that state. So I know that the work energy theorem says that work is equal to the change in kinetic energy. All right. Now, change in kinetic energy is going to be 1/2 mv squared. I don't need to do a delta v there because I start from rest. So I'm just going to substitute my expression for work into this. So that's going to be mg over L, or mg over 2L times y squared is equal to 1/2 mv squared. All right. So now I've got my expression here, and this m is actually capital M, so I'm going to change that. Now I can solve for v. Okay, so that actually makes our life pretty easy here. The m's are going to go away. The 1/2 is going to go away. And so what I've got is y squared over L is equal to v squared. And so all this is going to give me, and I'm sorry, there's a g here as well. Take the square root of both sides, and I'm going to get radical g over L times y is equal to v. All right. Work energy theorem there. You could have done that with forces and kinematics. I think it's a little bit harder. In terms of points here, you get a point for this relationship. You get a point for substituting your expression in, and you get a point for substituting m into this. If you just substitute correctly, guys, you're going to be fine. Final part, part E. The hanging block and the right end of the rope are each allowed to fall a distance L. The string is long enough that the sliding block does not hit the pulley. Indicate whether velocity from part A or the velocity from part D is greater after the block and the end of the rope have traveled this distance. Okay, so this is a tough question here. The answer is that the speeds are equal. Now you need to justify that because just getting that answer correctly only gets you 1 point out of 3 here. So how do we justify the fact that the speeds are equal here? Well, you could try to reason through this. I like to think about things mathematically. All right, so we have two expressions here. We've got an expression for v from the original problem, which is that vh is equal to radical gd. And we have an expression from this problem, vr, which is that v is equal to g over L times y. For this problem, we're looking for the case where the block and the rope are each allowed to fall a distance L. All right, so that means that in this expression right here, d becomes L. So after it falls a distance L, the velocity is equal to radical GL. All right, let's do the same thing here. Let's substitute y or L in for y. So this is going to be g over L times L, which this is actually just going to turn into radical g times L. That's this. That's this. These are equivalent to each other. All right. All you need to do is just test that extreme case, plug in, and see that they're equal to each other. And for this, guys, for that justification here, you're going to get 2 points. 2 points for that justification. All right. So there's 2009 FRQ number 3. Let me know if you guys have questions. Have a great day.